teletype. Here's WWV at 25 megahertz. At 15 megahertz. At 10 megahertz. Let's bring the gain down a little bit. And at 5 megahertz. Yeah, not quite getting him at 5, but he is there. So as we finish up this weather map, I can see this is probably CHU down here. Let's move down there. Yeah, it's nice to see signals coming in on 160 meters now. Could not do this on the dongle itself.
But I must get on with the day. Got things to do, no place to go. But that's okay. It's only going to last a few more weeks. Wednesday I get my second shot of the minus 70 degrees C, really cold Pfizer vaccine.
All right, 2 S points from the Roger. 2 S points. Wow, that's significant. Okay, and you're sounding about the same on both. You're about an S9 to a little bit over an S9, but that's good. Duly noted that the loop is a little stronger with DX. So.
Yeah, this FT8 really works very well. Yeah, it really pepped it up. Having that post amplifier, we've even got good signals coming in on the CB band at night. And it's quite amazing how bringing a low noise, high dynamic range amplifier after that passive mixer has made a difference. But there is too much gain, and I had to take the gain control almost down to 0 at the 80 and 40 meter bands. I'm only up about, maybe a third of the slider up here at the highest part of the band. But a lot fewer spurs since we shielded that filter, and once I get the oscillator filtered, I think it'll improve even more. So in part 3, I have a pretty good circuit developed, one that I think I can get a schematic out for you guys, and we'll be able to play with this thing as people try to build it up, and we'll have some comments and criticisms on the final schematic. So I did want to bring up a few books that are important to this type of solid state design, which I don't do that often, but this is a little more involved project. The old amateur ARRL Amateur Radio Handbook, very important. They have some other publications like Experimental Methods in RF Design. This is an excellent book, and it's got some famous authors that you're all probably familiar with. This is an old Howard Sams classic, a little bit dated now. It basically takes you through matching circuits and filters, RF circuit design. A classic if you're designing especially RF power amplifiers. Here's another one, an ARRL UHF microwave handbook. This guy's got a lot of tips when you get above, 1,000 megahertz, things get a little tricky. Now, this is kind of the granddaddy of the ham radio QRP movement in probably the 80s. This is Secrets of RF Circuit Design by Joe Carr. And you started seeing it in ham magazines, you started to see it in the handbook. Everybody was building with the 602, and it came out of this book, but there's a lot more than just that in this book. This is a really first principles type RF design handbook, basically written in an engineering technician language rather than an engineer's mathematics language. You got to get a hold of this. Or even better, get a hold of the second edition hardcover. This baby is something that you might want to collect. I want to do a spur search on just the USB dongle alone with a 50 ohm load on the input, not connected to any antenna, hooked up to the laptop alone, and I'm going to look for spurs. This is going to be my baseline search. I'm starting down in the broadcast band. I'm just going to try to record all the spurs I see. I see one right here, and it actually has modulation on it, so something's sneaking in at 1380. I'm going to list those spurs, so that's a starting point. The SDR-RTL has an instantaneous bandwidth of 2 megahertz. So after the tuner, 2 megahertz is presented to the A to D. So when we're tuning, we can only look at 2 megahertz at a time. Now I'm in the next swath. I went from 0 to 2 megahertz and found just one station. Here in this next 2 megahertz segment, from 2 to 4 megahertz, it looks like I have 2 spurs I need to record. So it's apparent that there are some inherent spurs in the NE SDR Smart, and when I turn on my oscillator with the front end converter, even though there's no antenna attached, there are some strong enough AM signals that are coming in, just being picked up through the board, through the grounds, that these will mix with the oscillator spurs, and you will get some new spurs showing up. So I'm going to turn power on. Dummy load input, no antenna, just turning the power on the oscillator. And this slice I'm looking at is basically the 31 meter band, and you can see those new spurs that have suddenly arrived. That has to do with the cleanliness of the oscillator, the shielding, and the filtering. So we're getting some intermodulation mixing occurring between some of those AM stations and the spurs of the oscillator itself, and they're creating new frequencies that we're seeing. Before I go any further on trying to improve the circuit, let's see how good our filter is on the front. I know that any of these filters are going to be compromised without proper shielding over them, and there is no shielding on this filter. Also, I haven't taken great care in the grounding. I probably should stitch a few through-hole grounds from the top ground plane to the bottom ground plane, just to get rid of some currents there. But before we start, I just wanted to see what the relative attenuation is when I'm going for, say, you know, the 80 meter band. I have a very good receiver here. This is a Watkins-Johnson receiver, and it's calibrated in dBm. And I've got it right in the middle of the paint where it's I've got some attenuation in. And I just set it up at the bottom of 80 meters. And let's see how many dB down it is when we get down to, say, 1 megahertz. See if we got some rejection. So we'll set this for 1 megahertz. And then we'll take this guy down to 1 megahertz. And the problem is I don't think I can hear it. It's there, but it's barely perceptible. So there's no doubt that the filter's doing a pretty good job. So we can't blame things too much on the front end filter for the AM broadcast band. Also, this is a test that you want to do up close to the top of the band as well. So let's go up to 1.8 megahertz. Actually, top of the broadcast band, 1.5 megahertz. Ah, here we go. Okay, so we're hearing something there. So the filter is down, let's see, 60, 20, 30, 40 dB. It's down about 40 dB from 80 meters to 1.5. So it's probably, you know, something 30 some odd dB down from the very edge of the band in 160. So the way I'm measuring this is I have a 10 dB pad up front to make sure the front end's terminated properly. And on the back end, I'm going straight through the mixer, pretending the mixer is online. And also, you want to have the oscillator on, because as you can see, when you turn on the mixer, it allows the diodes to conduct, and you will get some of the bleed through that we're trying to fight here. So you want to turn the mixer on with the local oscillator to do this test. Anyway, this is just showing the quality of the front end filter on the low end. So speaking about filters, why do we put good quality filters under shields? Now you can see the way that this particular filter has been designed. This looks like a 70 megahertz filter. It's got a bunch of adjustable coils inside, and it's a single layer board. There's no ground plane in the bottom. And the bottom is where they did all their connections. It's got a ground plane on top, and they've got a shield soldered on top of the ground plane. So that's a pretty fancy filter box. I want to do something like this on there to eliminate the possibility that the broadcast band or the FM band is coming around and coupling into the filter elements themselves before the mixer. So let's get a shield on. So for shielding material, certainly aluminum would work okay, but you're going to have to mechanically attach it because aluminum's not going to solder very well to this copper board. You can use copper circuit board itself. Just cut chunks of this and sweat solder, you know, the shield right on top. What I like to use is steel flashing, like you use you know, underneath roof eaves. It's very, very cheap and thin, and it solders quite nicely. Okay, some of you are probably making fun already, but there's a pretty nice old shield that's going to go over the front end filter. This is going to give us some proper isolation up front so that filter can do its work. I now have the shield on. I'm repeating the test with the mixer local oscillator on, and I definitely picked up about 10 dB at 1500, and at 1300 it's barely perceptible at all. So I think the shield did help some, and worthwhile addition, having the shield over the filter. So the next step is to add an amplifier to try to give a little bit of gain to the mixer stage. And the question is, do you want to put the amplifier before the mixer or after the mixer? So either right in here after the filter before the mixer, or right after the mixer. And I decided to go with the conservative approach, which is to use the post-mixer amplifier. If I didn't include this circuit, I would have been ridiculed by just about everybody, because this is the circuit that's been promoted for many years, starting with Hayward, McCoy, even Jack Lau, and on and on and on. And everybody has, you know, changed a part and patented it and copyrighted it and declared it their own. But really, this maximum current, maximum feedback type bipolar amplifier has been the go-to one-size-fits-all strong amplifier with a decent noise figure that everybody uses in these applications. So, hey, I'm going to go with it and build up one of these 2N5109 amplifiers, and we'll see how it operates. You can see a couple of things here. You can see that there's a pad right at the output of the amplifier to give it a little bit of stability, because the feedback is coming right into the bass, and that could tempt a little bit of oscillation trouble if the SWR got out of hand. This does terminate the mixer quite well, so along with my diplexer, I think this will work pretty well. So here we go, the 2N5109 classic bipolar strong post amplifier. This little broadband amplifier developed by Hayward and Dumas provides a nice 50 ohms in and 50 ohms out impedance across a wide bandwidth, and it exhibits excellent dynamic range and a good noise figure. These are rare to be found together all in one simple circuit, and it really has passed the test of time. This circuit's over 35 years old. Now, can you use a 2N2222 or a 2N3904 in this circuit? Actually, I would suggest not, and here's why. First of all, these transistors do not have a high enough transition frequency to take advantage of the feedback in this high IF range that we're using them. Might work okay at HF, but not as much up here. Secondly, they will not be so forgiving in terms of handling a lot of Class A DC current. And finally, their noise figure is certainly going to be higher up here. You can use substitute RF transistors, and these are RF transistors that are usually used for the middle and final stages of RF amplifiers. The 2N5108, 3866, 2SC1365, 1252, BSX20, NTE473, and the 316 series. Those are all good TO5 choices. The 2N5179 is a smaller transistor. One or two of those in parallel would make an excellent post amp. Remember, smaller transistors are going to need heat sinks. Even these TO5s really should have a heat sink if you want to run above 25 milliamps. What about surface mount parts? Well, yeah, you can use surface mount parts, but you're still going to need beefy RF transistors, like in SOT89s, like the 2SC3357 and its brothers. And the older MRF 580 series, like the 581 in the Macro X package, an excellent choice in this circuit. As far as the transformers go, the Type 43 ferrite cores work very well, but you can also use binocular cores in 43 and 73. And there's some pre-packaged transformers from mini circuits that work perfectly as is. Remember, if you're going to build with surface mount, use big resistors like 805s and 1206s to handle the current. But why would you build the amplifier in surface mount? What I mean is, even with SMT parts, it's going to take up your whole thumbnail. So it doesn't make a practical solution even for a production part. Today, we would use MMICs, microwave monolithic ICs. These things are available all over the place. They can do the same as this amplifier and even do it better with fair ease, less space, less cost. Of course, seriously, unless you're manufacturing upconverters for profit, what fun is it to use a MMIC? Let's slowly go through this one more time. In here we have our bandpass filter, which consists of a sharp high-pass filter that eliminates the AM broadcast band, and a low-pass filter that cuts in around 30 megahertz. I've added a shield, and this has really improved the isolation and the performance of the filter. And then going into a level 7 mixer. The level 7 mixer is fed by a 3 dB pad going into the LO port. I've got a low-pass filter going into the pad, which filters the oscillator, which we covered in the other video, which is a simple harmonic overtone oscillator that gives us our 40 megahertz LO. The low-pass filter probably gives 20 more dB of rejection on the second harmonic and more than 30 dB on the third harmonic. Coming out of the mixer, in this case we're using the mixer backwards, so this is the RF port. we have a high-pass, low-pass termination working as a kind of a wideband diplexer. So there's a capacitor going to a 50 ohm resistor going this way, and a resistor and an inductor going to ground this way that terminate the filter at the very low and the very high frequencies that we're not interested in. And then to the output we have a coupling capacitor that feeds a strong post-mix amplifier. This amplifier has been optimized to work above 30 megahertz. So the bifilar wind on the collector coil, which is essentially a center-tapped transformer, has only 5 turns. So this is made for the higher frequencies. Otherwise it's biased fairly lightly with about 20 to 25 milliamps going through the 2N 5109 transistor in a conventional strong amplifier. Coming out of the amplifier, we have another filter. This time it's a high pass cutting in around 40 megahertz that eliminates any, again, fighting more broadcast and strong stations from getting into the IF passband. And then finally a trap to ground. This trap to ground, I was thinking of using a crystal with it as well to take out the local oscillator residual. And then a bypass capacitor going to the output, because we know that the Smart can produce bias. I wanted to make sure bias couldn't go either way. I also have a 6 dB pad on the output. I find that this is useful at night when especially the low frequency signals between 3 and about 10 megahertz start to really get strong. You can add padding here just before the Smart. The SDR-RTL is easily overloaded, so adding a pad here can help with the dynamic range. So that's the final product. I think I would add a trimmer to the crystal here, perhaps shield the oscillator, and it might improve any oscillator bleed through even further. So I don't know if you guys call these diddle sticks or tweakers, but I wanted to show you that I put a small trap right at the output of the converter. Now that trap would probably do better before the amplifier, right at the output of the mixer, rather than at the very end just before you're feeding the RTL-SDR. But I wanted to show you what a trap can do specifically against the 40 megahertz local oscillator bleeding through into the receiver. So that 40 megahertz is really zero frequency as far as we're concerned with the upconverted band, and so 41 megahertz would represent 1 megahertz, and we're interested in stuff that's above 1.8 megahertz. That's not very far from zero, so that oscillator just comes right through as a gigantic signal, and that's not helping the dynamic range. So let me put a tweaker on the trap and see if I can lower the oscillator from sneaking through. Okay. Looks to me like I easily got 20 dB. Now maybe not 20, but I at least got 15 dB of rejection, even with the trap being at the very end of the whole deal. I think it would be even more effective at the output of the mixer, but that's what a trap can do against local oscillator bleed through. This little device is a manual attenuator. If you find something like this at a ham fest or flea market or online, you definitely want to build it, or you definitely want to buy it, because this allows you to put in attenuation and it works up to very high frequencies. This one's DC to 1 gigahertz. This one is a very nice manual attenuator, and you can put in everything from half dB to 30 dB steps. Now, a lot of these have taken damage over the years, and they might not be absolutely accurate because they've seen too much power, but still a nice thing to have on the bench, and a lot of them are repairable. So what we want to do is use this manual attenuator and see where the most effective place to put attenuation is to maximize the dynamic range. Do we want to attenuate right at the antenna? Do we want to attenuate right into the RTL-SDR? Or do we want to insert the attenuation for the mixer? Those are three places that we can explore with this manual attenuator and see where we can gain the most dynamic range without spoiling the sensitivity of the circuit. For this attenuator overload test, I'm going to be using the 2 megahertz section just below the 80 meter band that includes CHU as my test signal. Now, with all of the gain that we have in the converter with the post amplifier and the attenuator on the input side, on the antenna side, I'm now going to increase the gain using the slider until I get obvious overload. Okay, there we go. So I've got 25 dB of gain in, and we have all kinds of intermods happening. We're definitely overloading the dongle, you can see that easily. So now I'm going to start putting in some attenuation. So here's 10 dB. Now with 10 dB in, signals went down, but I still have a lot of intermod. Let's take the 10 out, put 20 in. 20 is a little better. Let's try 30. 30, probably still have some intermod showing. 40. 46. So you get the idea. We're reducing the attenuation on the input, but we're also reducing our signal drastically. The next place I'm going to put the filter is just after the mixer. Okay, next I've put the attenuator right after the mixer. So basically right at the termination port before it feeds the amplifier. We're picking up a little more intermod because these wires act as antennas. You can see how sensitive the circuit is. But we'll do the same test. Let's put in 3 dB. Now 6. Notice how it's calming it down almost immediately with just 6 dB. 10. 20. Now, notice how it's more effective and we're not losing the signal to noise ratio. I've got 20 dB in and it's completely eliminated the intermod, but we haven't lost our signal to noise ratio. So this is obviously a better place to put an attenuator. Okay, here's the final place that we can put the attenuator. It's after the amplifier. It's right at the absolute output of the converter. So this is equivalent to putting a pad at the output of the amplifier like shown up here. Okay? just because we're on the final port, the output port, that doesn't mean it doesn't kind of represent this. It would be better if it was back by the transistor though, so keep that in mind. Putting a 3 or 6 dB attenuator right after the amplifier is probably a good idea. Let's see what we can do to this intermod. Okay, let's try 3 dB. 6. 10. This is 10 dB. And the 20. Little more noise than putting it just after the mixer, I think, but also a good place to put an attenuator compared to the very front end at the antenna. I've got 20 dB in now. Let's go back to 10. So maybe a 15 dB pad there would settle it down. At this high gain level, you'd never run this high gain level normally. You'd back that off until you cleaned it up, but sometimes you just can't. So you need to put attenuation in there. So the next question should be, Mike, I have a converter that I take the bias out of the front of the RTL-SDR, and I can't put an attenuator in there. It'll short out the DC, and I won't be able to power my amplifier. It'll short out the DC. I won't be able to power the converter. It comes right through the front of the dongle. Well, then you need to build a bias passing attenuator. That's right, an attenuator that passes DC with no loss, or very little loss, but allows AC signals, like the signals that we're listening to now up at this high frequency, to be attenuated 6, 10, 20 dB. Well, we clearly have a new ball game here now. Got too much gain, I think, but I've done quite a bit. I know that you guys would never forgive me if I didn't try to do a post amp at least after the passive mixer.
It's 5 minutes to midnight, and we have today lovely conditions, lovely weather conditions, blue sky and sunshine, and the temperature 70 degrees. Much like you, Victor Ocean 1, Mexico, Italy, Foxtrot Farm, Bravo Echo Whiskey, listen.
Now, some of you are probably looking for detailed coil winding information, a complete parts list, detailed schematic, high resolution, everything. This is not the place to get that. I maintain a Facebook page called the Radio Resource, Microwave One Radio Resources. And this Radio Resource page is where I will have all of the detailed information to actually try to build this circuit. Putting it on a video doesn't really work out. In the next video, and there is one final video coming, we're going to try some different tricks with the circuit. I would really like to try a pure square wave local oscillator approach. Okay, we need to light up that mixer with a square wave. And I also would like to see what would happen if we could put a variable attenuator in the circuit, something that we could adjust externally to do some of this attenuation we've been doing with the flip switches. So stand by for the final video on the SDR-RTL front end HF upconverter.